Welcome back to this series of Power Electronics Labs. Today we will go through Lab 8, DC-DC Converter. The contents are 1. Introduction, 2. Circuit and principle, 3. Building prototype, 4. Testing results. Now let us start with the introduction. The purpose of this lab is to 1. Build a prototype of half-bridge converter, 2. Use it as a buck converter first, and then as a boost converter. Buck converter is a step-down DC-DC converter. Its control component is the MOSFET at high side. Adjusting the duty cycle of the high side MOSFET controls the output voltage. Boost converter is a step-up DC-DC converter. Its control component is the MOSFET at low side. Adjusting the duty cycle of the low side MOSFET controls the output voltage. Now let's look at the circuit of the prototype and its working principle. The prototype consists of two portions: 1. Power section, 2. Gate driver. The power section includes a half bridge plus an inductor. It has two terminals, VH for high voltage, VL for low voltage. Capacitors are used to smooth the voltage level. The gate driver uses a pre-designed integrated circuit IRS-2104. It takes the PWM signal from Lab 7 as input, and provides two gate signals for the half-bridge MOSFETs. For the high-side MOSFET, the gate signal GF1 carries the same duty cycle D as the input PWM signal. For the low-side MOSFET, the gate signal GF2 carries a duty cycle 1-D. A bootstrap circuit as shown D2. EC7 is used to supply a floating power source for the high-side MOSFET gate. Now let's look at the working principle of the prototype. The same half-bridge converter can be used either as a buck converter or a boost converter. For buck converter, the terminal VH is used as input, which will be connected to the power source. The terminal VL is used as output, which will be connected to the load. The output voltage is proportional to the high side duty cycle D. For boost converter, the terminal VL is used as input, which will be connected to the power source. The terminal VH is used as output, which will be connected to the load. The output voltage is inverse proportional to the high side duty cycle D. Now let's build the prototype. First, find the components for this lab. The PCB portion. Lab 8 DC-DC converter. 6 surface mount resistors, R36, R37 or 5.1K, R38, R41 or 10K, R39, R40 or 15 ohms. 4 aluminum capacitors, EC4, EC5 or 100 microfarads, EC6 is 10 microfarads, EC7 is 1 microfarads. 1 diode, 1 inductor, 2 MOSFETs, 1 DIP8 IC socket, 1 IC, IRS-2104. The recommended procedure for soldering the components are: Step 1 to 6 surface mount resistors, R36, R37, R38, R39, R40, R41. Step 2. The diode. Step 3. The DIP8 IC socket. Then insert the IC IRS-2104 into the socket. Step 4. The inductor. Step 5 to 4 aluminum capacitors, EC4, EC5, EC6, EC7. Now the prototype is completed. Now let's test the prototype and get the results. First, let's set the prototype as a buck converter. From an external power supply, connect 12 volts to the input terminal VH. Connect a load resistor to the output terminal VL. Use an oscilloscope for measurement. Connect channel A to the output terminal VL. Connect channel B to the PWM signal from Lab 7. Here is a captured waveform. Measure output voltage, PWM frequency and duty cycle. Now we can verify that the output voltage is proportional to the duty cycle. Here is a video clip showing the output voltage changing along with the duty cycle. Now let's set the prototype as a boost converter. Connect 5 volt source to the input terminal VL. Connect a load resistor to the output terminal VH. For measurement, channel A measures the output voltage VH. Channel B still measures the PWM signal. Here is a captured waveform showing the measured output voltage, PWM frequency and duty cycle. Now we can verify that the output voltage is inverse proportional to the duty cycle. Here is a video clip showing the output voltage changing along with the duty cycle. We complete the lab. Thanks for watching.